In this video, I'm going to talk about a new type of dual-fuel burner that runs on natural gas and generator gas at the same time. Or, if you prefer, on natural gas and, when necessary, on generator gas. This is basically a rarity and something almost unreal. If you call the scientists who design burners and ask if they can make a burner that runs on natural gas, and when required, on generator gas, 6 times less caloric, and with 5 times bigger mass, using the same nozzles, they will make a cuckoo sign. But as for me, the authors of the work I'm telling you about made it. I have to say that only a few inventors develop non-standard burners. I developed generator gas burners and test them myself. In the past, when my knowledge was still insufficient, I had to find someone who would make such a burner. You would be surprised, but there are only a few companies that can undertake the development of burners in the entire post-Soviet space. However, no one will make developments for an adequate price. It took me several years to solve this problem. Let me give you a couple of examples of my negotiations. In one company, the director told me with hysterical notes in his voice that research and development to create a prototype will cost 20,000 euros. He also told the legend that eventually it's not going to work at all. Another company put a price of $200,000 for a half-megawatt burner. Here I am not mentioning the dozens of old tinkerers, Smiths, Johns, and Browns who seem to make good burners and are very handy and brainy, but only God knows how their burners will work as a result, and what their designs are based on. Why is it so expensive, and why can only a few people make burners for non-standard gas? It is expensive because a good quality burner requires very serious research. You may say, what's the big deal? You make an ordinary swirl burner, and that's it. But we have to understand that gas underburning lead to big losses. Just bring a gas meter to a burner and see the percentage of unburned gas. If the burner doesn't burn the gas fully, the precious fuel circles the drain, pleasing the environmental inspector. Besides, the fuel is consumed excessively. If swirl burners were that good, then all the existing industrial burners would be of this type. But they aren't. Generator gas, especially non-purified, burns worse than natural gas. It has a sluggish flame front and it is ballasted with water, nitrogen, and carbon dioxide, which leads to constant flare failures. Carbon dioxide, its content is about 10%, negatively affects the flare. Therefore, a good quality generator gas burner is a problem. When I talked to industrial plant owners, they often wanted to add generator gas to the natural gas burners they were running or feed natural or generator gas to the same burner. But what will happen if they can't find fuel for the gasifier and would like to run a plant on natural gas one day? Wouldn't they change the burners every time, would they? That's a big problem. So, I was very interested in the following research, and I decided to take a closer look at it. And guess what? Its authors did manage to make it. They conducted tests at a steel mill where it was necessary to save on natural gas on 3 burners of 400 kilowatts each. The burners were fed either a mixture of natural and generator gas, or one or the other gas alone. Generator gas is 20 to 30 times more profitable than natural gas, and probably even more in some countries. Plus it has an environmental advantage. Its combustion temperature is about 1,100 degrees, so it produces much less nitrogen oxides than natural gas with a flare temperature of 1,600 degrees. Not to mention that gasification is a green technology limiting additional CO2 emissions compared to fuels extracted from the Earth interior. This is a recent scientific paper from 2020 based on the results of a number of long experiments. At first, the scientists decided not to change the burner and simply added 10% of the generator gas to natural gas. It turned out well, which was confirmed by other scientists' tests. But 10% of the generator gas did not save much money. It was necessary to add more, but it turned out that adding up to 40% of generator gas required a completely different burner. It was necessary to supply 4.7 times more generator gas by mass than standard gas, which means increasing resistance of the burner because of its narrow nozzles. The researchers had a conventional wood-fired downdraft Embert gasifier with an approximate gas caloric value of 1,100 kilocalories per 1 cubic meter. The caloric value of natural gas is 7,600 kilocalories per 1 cubic meter. When 40% of the generator gas was added, the standard nozzles had too much resistance. It exceeded 10 kilopascals while the design resistance should not have exceeded 4.5 kilopascals. Then the researchers decided to modify the existing burner. It is shown in the photo. The average composition of the generator gas was taken as the basis for the supplementary gas. In reality, its composition differs because of the differences in fuel and its size. The calculations are based on average gas composition. The air-gas mixing ratio was taken as 1.05. 3 options were considered: increasing the diameter of the existing nozzles, adding a gas duct around the existing one, or an additional air duct around the existing one. Due to space constraints, the researchers took the second option. They began to supply gas through an additional duct, figure 14. Tests showed a stable flame, table 7. The scheme is shown in figure 15. But it still did not work as it should. Based on test results, the researchers realized that conventional natural gas burners could not work well on a mixture of natural and generator gas. It was necessary to develop a new burner from scratch. It must operate not on 40% added generator gas, but on 100% natural gas or 100% generator gas. And the generator gas had a temperature of 300 degrees while the air fed to the burner was 20 degrees warm. On some days the system should be able to work on natural gas, and on others on generator gas. At the same time, the burner should not be changed. Figure 18 shows a new burner design. This was a 90 kilowatts test burner with natural gas fed through a tube into the center and coming out through 4 holes. They are shown in red in the figure. The holes are 3 mm in diameter and beveled at 45 degrees to the sidewall. Primary air is supplied through a tube 19.8 mm in diameter. The diffuser and probe are immersed 20 mm deep in the stone. Generator gas is fed through the tube marked in green in the figure. The outer and inner diameters are 56 and 25 mm. Secondary air is supplied through the circumference, shown in dirty yellow. The outside and inside diameters are 81 and 68 mm. The 45-degree blades swirl the secondary air to create a vortex for better mixing with the gas. The new burner was tested at the Institute of Energy on the bench. Figure 19 shows the results. The burner showed flexibility and worked at capacities from 20 to 90 kilowatts. Figure C shows what happens if the burner runs on 2 gases, as I understand, 50/50ths. Figure A shows the results of adding 70% generator gas to 30% natural gas, 2 combustion zones formed. Figure D shows what happens when mixing 30% generator gas with 70% natural gas. Table 8 and Figure 27 show the test results. A stable flame was achieved at different burner loads from 19 to 91 kilowatts. The results of the co-combustion of the 2 gases are shown in Table 9 and Figure 28. Based on the results of successful laboratory tests, 3 400 kilowatts burners were made and installed in the steel foundry preheating furnace. The generator gas lowered harmful emissions and saved considerable money.